previous video, we were discussing about the rule 3, segment of real axis having an odd number of real axis open loop poles and zeros. That means total number of including both zeros and poles. To the right are parts of the root locus. So this I was explaining. This figure you can see that if you are taking this segment, to the right of this segment, you can see that 1, 2, 3, 4, 5. There are total 5 that means 3 poles and 2 zeros. So total 5 items are there, or 5 poles and zeros. So it is an odd number. So this segment is included in the root locus. Here it is not, because right of this 1, 2, 3, 4. So it is not an odd number. When you are considering this segment, right of this there are 1, 2, 3. So it is included. Here if you are considering this segment, if you are considering right of this there are 2, it is not odd number, so it is not there. Now when you are coming here, when you are coming this segments, right of this there are 1, so this is included. And you can see the you should rule 2 you should remember. Now from the pole the root locus starts and end to nearby zeros. It will start from pole, it will end to 0. This there is no 0, that is why this will go to the zeros in infinity. So this is a good example to understand. Now each pole and zero on the real axis to the right of any point on the real axis contribute an angle 180 degree with respect to that point, and each pole and zero on the real axis to the left of any point on the real axis contribute an angle of 0 degree with respect to that point. The net angle contribution of a complex conjugate pole or a zero is always 0. So this you can understand from this diagram. Now here you can see that here one pole is there, here one pole is there, here one zero is there, and here one pole is there, here one zero is there. Now if you concentrate on S naught, now so the angle contributed by this 0 with respect to this point is 180 degree. To the right of this, angle contributed by this pole with respect to this is again 180 degree. Angle contributed by this pole with respect to this is again 180 degree. Now the angle contributed by this pole, that is located left of this reference point, it is 0. Angle contributed by this 0 that is located left of this point is 0. So that is why each pole and zeros on the real axis to the right of any point on the real axis contributed an angle of 180 degree with respect to that point, and each pole and zero on the real axis to the left of any point on the real axis contribute an angle of 0 degree with respect to that point. Next, the net angle contributions of a complex conjugate pole or a zero is always 0. Now, you can see that net angle contributions of a complex conjugate pole. So, this is a complex conjugate pole. A complex conjugate 0, let us assume that 0. So, the angle contributed by this is 0. Now, this will already I had given the explanation of this. There are 3 poles. One is at s is equal to minus 6, this is x is at minus 5, and this is s is equal to minus 1, and here there are 2 zeros. One is at s is equal to minus 3 and s is equal to minus 4, and that is explained in this and how the root lock is happening. The same thing also here root locus is symmetrical about this axis, because all that is rules 1. There are because there are 3 poles according to the rules. There are 3 poles. There are 3 branches of root locus, and 2 will end with the zeros of zeros at minus 4. Wait for some time. What is this? Yes. Yes. So here you can see here there are as you can see that there are this poles. The root locus starts from this poles end here. This pole start from here end here. This pole there is no corresponding zeros, so it will end to a 0 at infinity. So that is a yes. As k increases, the root locus branches leave the open loop poles and go to the open loop zeros. 2 branches terminated on the 2 open loop zeros, and the third one terminates on the infinity. The real axis segment between s is equal to minus 1 and s is equal to minus 3, and s is to minus 4 and s is to minus 5, and s is equal to minus 6 and s is equal to infinity lies on the root locus. That already I explained. Now, rule 4. The n minus m branches. N is the number of poles, m is the number of zeros. So that this is rule number 4. The n minus m branches of the root locus which go to infinity travel along a straight line. Asymptotes go to infinity travel along a straight line. Asymptotes whose angles are given by theta q is equal to plus or minus 2q plus 1 pi divided by n minus 1. Q varies from 0, 1, 2 till n minus m minus 1. So here, what you can understand here is that sum of the branches, it will go to infinity, and which go to infinity travel along straight line. Travel along means it will parallel to some straight it will close to some straight line, asymptotes whose angles are given by, this is the angles of asymptotes. Then what is an asymptote? Asymptote is a straight line that continually approaches a given curve but does not meet it at any finite distance. Once more I'll tell what is asymptote. Asymptote is a straight line that continuously approaches a given curve. Continuously approaches a given curve. It continuously approach but does not meet it, and it at any finite distance. In any finite distance, it won't coincide, but it will constantly approach. That means it will go in parallel with, but it won't meet with the curve that is known as asymptote. So this finds the angle of asymptote. Now consider any point on the branch of the root locus which is far away from the open loop poles and zeros. The phasors are drawn from such a point to all the open poles and zeros. Make the same angle theta to each open loop pole and zero. Therefore, at the point consider the g of s, the angle of g of s h of s is equal to minus n minus m theta. For the root locus to exit at this point, minus n minus m theta is equal to plus or minus 2q plus 1 pi. Since n minus 1 branches of the root locus go to 0 at infinity, the angle of asymptotes are delta q is equal to, already told, plus minus 2q plus 1 pi divided by n minus 1. Q varies from, okay. So now consider any point on a branch of the root locus which is far away from the open loop poles and zeros. The phasors drawn from such a point to all the open poles and zeros make the same angle theta to each open loop poles and zero. Therefore, at the point considered, this is during example you will understand the angle of g of s into h of s equal to minus n minus m theta. For the root locus to exist at that point, minus n minus m theta is equal to plus or minus 2q plus 1 pi. Now, the rule 5, the asymptotes cross the real axis. Asymptote means not real root locus. It is a straight line almost parallel to the root locus curve. So here asymptotes cross the real axis at a point known as centroid, determined by the relationship. Centroid is calculated with the, normally it will come to the negative side of the real axis, that is why it is negative sigma, that is equal to sum of real parts of the poles, minus sum of real part of zeros divided by number of poles minus number of zeros. So sum of real parts of the poles minus sum of the real parts of zero divided by number of poles minus number of zeros. Finding the centroid. Rule 6. The breakaway point and break-in points, point at which multiple roots of the characteristic equation exists, point at which multiple roots, that means breakaway point and break-in points, point at which multiple roots of the characteristic equation exists, of the root locus are the solution of dk by ds is equal to 0. So dk by ds by 0. So that you will also, when we are doing the problem, you will come to understand. Now the breakaway point and break-in point may be a real or complex. Break angles. The root locus branches must approach or leave the breakaway point on the real axis at an angle of plus or minus 180 degree by r, where r is the number of branches approaching or leaving the break point. So here, in order to find the breakaway point and break-in point of the root locus are the solution of dk by ds, and the root locus branches must approach or leave the breakaway point of the real axis at an angle that can be calculated by plus or minus 180 degree by r. This is the rule 6. Now we will first see all the rules. Now the rules number 7. The angle of departure from an open loop pole is given by theta d is equal to plus or minus 2q plus 1 pi plus pi, where q varies from 0, 1, 2, where pi is the net angle contribution at this open loop pole for all other open loop poles and 0. Pi is the net angle contribution at an open loop pole of all other open loop poles and 0. Similarly, angle of arrival at an open loop 0 is given by theta a is equal to plus or minus 2q plus 1 pi minus pi, q varies from 0 to 1, 2, where pi is the net angle contribution at this open loop 0 of all other open loop poles and zeros. Now here you can see how the angle of departure, angle of calculation of angle of departure, we will look into this. This is the angle of departure. This is a pole, complex conjugate pole. Here you need to find at what angle the root locus starts. Okay, at angle it starts. Now there are 1, 0 here, another pole here, complex conjugate, and another pole here. So you need to calculate the degree made by this pole with other all. Here it is 26.6 degree. 26.6 degree. This will be 90 degree. This will be 135 degree. 1 minute. Okay. So here it is theta 135 degree. Now in order to see the departure, you need to find first pi. Pi can be calculated with the angle created with 0, that is theta 3, minus angle created by two poles, that is theta 2 plus theta 1. So 26.6 minus 90 plus 135. So you are getting it as minus 198.4 percentage. Now theta d is calculated with the problem, plus or minus 2q plus 1 pi plus pi. So here when you are calculating it, here you need to take 180 degree. This is single pair, so 180 degree minus this pi only. So here q is equal to 0. So that is why 180 degree plus pi is minus 198.4. So it is equal to minus 18.4 degree. So here the angle of departure is minus 18.4. When you are coming to here, it will be plus. When it is minus, here it is plus 18.4. So normally the root locus will start departed from poles and it arrives at zeros. So next we will see how directly I am going to the example. Now if there are multiple poles and 1 0, that 0 angle you have to take it first, minus all the poles angle you have to add it and subtract it, and that will be you need to use to calculate theta d. So now yes, the calculation of angle of arrival, same way here there is 1 0 1 complex conjugate zeros, that means 2 zeros, complex conjugate zeros, and there is one 2 poles. So what you need to do is pi is calculated with the angle created to the zero only. Here also first you have to consider 0 minus pole, that is pi is angle created by theta 1 minus theta 3 plus theta 2. So 90 degree minus 135 plus 26 degree, that is equal to minus 71 degree. So QA should be calculated 2q plus 1 pi minus pi, 180 degree minus 71, it is 251. So this will be 251 and this will be minus 251. So this will be the root locus, it will arrive and it will arrive at this post. Here also the root locus will come and arrive at this zeros. Now the eighth point, the point of intersection of the root locus branches with the imaginary axis and the critical values of k can be determined by use of Routh criterion. So this is already we studied. The point of intersection of the root locus branches, point of intersection of root locus branches with the imaginary axis, and the critical value of k can be determined by the use of Routh criterion. So you know that if there are poles on imaginary axis, then the difficulty 2 arises. Normally the difficulty 2 arises. Okay, so we will take an example here. This is very easy to do it. For example, this is an open loop transfer function k divided by s into s plus 1, the s plus 3. You can see that here there are 2 poles, no zeros. S is equal to 0, s is equal to minus 1 and s is equal to minus 3 are the poles locations, and the the characteristic equation is 1 plus g of s into h of s. So when you are doing like that and multiplying these all terms, you will get the characteristic equation as s raised to 3 plus 4s square plus 3s plus k is equal to 0. You need to form the root table. Now, for all the roots of the characteristic equation to lie on the left of the imaginary axis, the following condition should be satisfied. That means all the elements in this column should be positive. So k should be greater than 0. 12 minus k by 4 should be greater than 0. So k should be less than 12. One is k should be greater than 0 and k should be less than 12. The critical value of k, which correspond to the location of roots on j omega axis, that is critical value of k, okay, correspond to the location of roots in the j axis is given by, when you are equating this to 0, 12 minus k by 4 is equal to 0, that is equal to k is equal to 12. Now the value of k is 12 makes all the coefficient of s raised to 1 row of the root table, this will become 0 and this will be 0. So you need to consider the auxiliary equation, that is 4s square plus k is equal to 0. Now substitute k as 12. So you are getting s square is equal to minus 3, s is equal to plus or minus j square root of 3, that is equal to plus or minus j 1.73. So thus for the root locus plot shown, we can see that it will be on J3, the root locus crosses the imaginary axis. Now the alternate way, the point of intersection of the root locus branches can be calculated. How you can calculate it? This is your, I'm directly going to the s square, s cube plus 4s square plus 3s plus k. Replace s by j omega and separate the real and imaginary parts. Now, when you are substituting here s cube j omega all cube 4j omega square plus 3j omega plus k is equal to 0. Now, in this j cube I can write it as j square into j square is minus 1. So minus 1 into j, I can say minus j omega cube. Okay. Once more I'll repeat, j cube is there. This will be, I can write a j cube omega cube. J cube is nothing but j into j square. J square is minus 1. So minus j into omega cube. Here 4 into j square omega square. So j square become minus, so minus 4 omega square plus here 3j omega plus k is equal to 0. Now the imaginary terms, equating the imaginary parts to 0. So equating the imaginary parts to 0, that means here there are two imaginary parts, j minus j omega cube plus 3j omega. So if you are taking minus j outside, omega cube minus 3 omega is equal to 0. So omega can again it can be taken outside. Then omega square inside the bracket minus j omega square minus 3 omega is equal to 3 equal to 0. That is omega square minus 3 is equal to 0. Omega is equal to plus or minus j square root of 3. And if you are equating the real parts, that is minus 4 omega square plus k is equal to 0. Now, yes, k is equal to, from this you are getting k is equal to 4 omega square. Omega is you are getting plus or minus j square root of 3. So omega square become plus 3. So 4 into 3 you are getting 12. So this is the, this is easy way to find an alternate method. Otherwise root locus criterion also you can use it. Now last rule number 9, the value of open loop gain k at any point S0 on the root locus is given by, you can calculate, okay, product of length of vectors drawn from that point S0 to all the open loop poles divided by product of length of vectors drawn from the point S0 to all the open loop zeros. So here it can be proved by like this. This is the characteristic equation. So g of s in modulus of g of s into h of s is equal to 1. So g of s, h of s can be represented k into s plus z1, s plus z2 like that is equal to 1. So modulus of k can be taken as this will come to the numerator, this will come to the denominator. So that is product of j is equal to 1 into n s plus pj poles and pi product of I is equal to 1 to m s plus zi, that is zeros. So that is product of phasor length from S0 to the open loop poles, product of phasor length from S0 to the open loop zeros. So these are the 9 rules. Now in the next video we will analyze some problem related to this.